Hey, good morning, guys. I apologize. I forgot to hit record on Monday, so I am re-recording what I talked about on Monday. Now, hopefully this will go a little better than that did, but you never know. So we had left off in the redox lecture talking about how to balance redox equations. So I'm not going to go back to those slides. I have posted the rest of the answers from those slides to D2L already. So all of that stuff has been posted. There are a couple of things in that lecture that I want to talk about today that were meant to be review, because I used to do this in the other order, but now I don't. So I'm going to want to refer to those as we go through today. So there'll be a little jumping around a bit, and I'll try and keep up, let you know where I am. So let's pick up with the next lecture, which is for Voltaic cells. Okay, so this is the lecture that we're looking at, and it says, and one of the things I wanted to review is what is meant by redox. So redox is a term that stands for reduction oxidation. And it implies that we cannot have one of these things without the other. So that's why we shove it into one word, because I can't have a reduction without the oxidation. I need the electrons from the oxidation to lose electrons oxidized. To then gain the electrons in the reduction. So gain electrons, reduce. So I cannot do the reduction without an oxidation. And I can't have an oxidation that produces more electrons that I can pick up using that reduction. So that's how that works. It has to go together. Now, there are other things. So there's Leo the line goes GER. That's the way I do it, which is lose electrons, oxidize, gain electrons, reduce. I've also heard of oil rig. So oil rig, which is oxidation is loss, reduction is gain. And so again, we need to think about where are the electrons in this thing. If they're a product, I have lost them. That is an oxidation. So here, my oxidation, E minus, is a product. In my reduction, I need to gain electrons to reduce. So that means that my electrons must be a reactant. Okay, so technically speaking, this all happens simultaneously, but those electrons have to come from somewhere to go somewhere. So that's how that works. Now I have two examples for balancing the following equations. One is in acidic solution, one is in basic solution. So I'm going to walk through how I did that. So I'm going to flip this over and show you that there is this solution that's already posted. Okay. What I did was, first step, always write my half reactions. So I have H3PO2, I'm going to H3PO4. That's one of my half reactions. The second one is Cr2O7 minus, going to Cr3 plus. And again, that came directly from what was on the slide, H3PO2 and H3PO4, Cr2O7 minus, going to Cr3 plus. So I just split the things I have so that it's like terms. Chromium stays with chromium, phosphorus stays with phosphorus. So those are my half reactions that I write from this. The next thing I do after I write my half reactions is I have to balance for anything that is not oxygen or hydrogen. So here we're looking at, do I have the same number of phosphorus on both sides? Which I do, so I just copied that down. And here I need to look at the chromium. Now I have 2 chromium on my left. I don't have 2 on my right, so I put a 2 out in front of that to then give me the same number of chromiums on both sides. So now I've dealt with chromium. Now I need to deal with oxygen using H2O. That's where I get that oxygen. So if I'm missing any oxygen, I'll add H2O. So looking at this equation right here, I can see that I have 4 oxygen on this side and 2 oxygen on this side. So I need to add 2 H2O to that half reaction, which is what I did. I have 7 oxygen here and none on this side. So I had to have 7 H2O here to make up for those oxygens. So now I've dealt with phosphorus, chromium, and oxygen. Next, we look at hydrogen. And we always do hydrogen with H plus after the oxygen because I add protons when I do the H2O. So I add that H plus or the H. And so I need to deal with that after the fact. Okay. So that's why we do it in that order. And we always do this, even if I'm in basic solution with this process. So there is another way to balance these using an OH. If you want to do it that way and you learn it somewhere else, that's fine. But I don't do that. I always do it the same process and then do a correction at the end for a basic solution if required. Notice that I wrote acidic at the top because that reminds me that I need to do this in acidic solution. If I wrote basic up here, then I know I need another step at the end. So H with H plus. So looking at this half reaction right here, I can see that I have 3 hydrogens there. I have 3 hydrogens there. But I also have 4 hydrogens from here. So I actually am short 4 hydrogens on this side. So I add 4H plus to that side of the reaction to take care of that. And looking at this, I have no hydrogens on this side, but I now have 14 that I added over here. So I had 14 H plus on this side of the half reaction to make that work. So now I have the same mass balance. I have balance for phosphorus, chromium, oxygen, and hydrogen. Now I have to look at the charge. So in this half reaction, I looked at what was the charge on this side, and I see no charge on this side. On this side, I have a 4 plus. Over here, I have 14 plus minus 2 is 12 plus. Here I have 2 times 3 plus is 6 plus. So I come down to the next thing, and of course I have to make this equal. So I need to add 4 electrons to this side of the half reaction to even out that charge. That's what I did here. Here I have a charge, I have plus 12 and plus 6. So I need to add 6 electrons to this side to make that even. So I did that. I added 6 electrons over here. Now the next thing I have to do is make the electrons the same. They have to have the same number of electrons. So since I have 6 in this half reaction, and I only have 4 in this half reaction, I need to multiply both of those to get to 12, my lowest common denominator. So I multiply this by 3 and this one by 2 to make that happen. So if we slide this up a little bit, hopefully I can do that. Oh, too far. Sorry. I end up with 3 H3PO2 plus 6 H2O goes to 3 H3PO4 plus 3 times 4 is 12 H plus and 12 electrons. So that's the multiplication on this half reaction. Doing the multiplication here, I end up with 12 electrons here, 16, 2 times 14 was 28 H plus. Sorry, I had already done the subtraction. So 28 H plus, and then 2 Cr2O72 minus. Then we multiply this by 2, we get 4 Cr3 plus, and 7 times 2 is 14 H2O. Now I can add and cancel. So I know that I have H2O on both sides. I currently have 14 here. I have 6 here, so I cancel the 6, and that leaves me with 8 on this side. I can cancel the H plus. I have 12 H plus here and 28 here. So if I cross this out, that leaves me with 16 over here. And my number of electrons are the same, so I cross them out. Then I pull everything down. So I end up with 3 H3PO2 plus the 16 H plus the 2 Cr2O72 minus goes to the 3 H3PO4 right here plus the 4 Cr3 plus plus the 8 H2O. Okay. So that is that equation, and that should be balanced. And so what I did next was to do my check on both sides. And so if I do my check for my hydrogens, I have 3 times 3 is 9, plus 16 is 25. I have 3 phosphorus. I have 3 times 2 is 6 oxygens here. And then I have over here 14, which gives me the 20. Okay, just making sure I remembered what that number was. I see that I have 2 times 2, 4 chromium. And then my charge on this side of the equation is 16 plus negative 4 gives me plus 12. So that's 12 plus, that's right here. On the other side of my equation, 3 times 3 is 9 hydrogens plus the 16, again, 25. I have 3 phosphorus. Here I have 12 oxygen, and then 8 over here gives me a total of 20. I have 4 chromium, and then I have 4 times 3, 12 plus as charge on this side of the equation. Okay, so that's all of my checks. Everything is good. This was, looking back at the top, oh, where'd it go? Sorry, didn't mean to close it. Looking back at the top, this was an acidic solution, so I am now completely done. So that's the first one. When I went to the second one, looking back at my slide, I have HO2 minus CrOH3 going to CrO42 minus plus OH. So the HO2 minus goes to the OH minus, and the CrOH3 goes to CrO42 minus. So second one, looking at the next page, if I can get to it. Okay, so my half reactions. HO2 minus goes to OH minus, and then CrOH3 gives me CrO42 minus. So those are my 2 half reactions. Second step, I have to balance for anything that is not oxygen or hydrogen. So I don't have anything except oxygen and hydrogen here, so I just wrote it down again. Over here, I need to make sure I still have the same number of chromiums on both sides, and I do. So I just wrote that down again. The next thing I do is oxygen with H2O. So looking at this, I have 2 oxygens over here, only 1 over here, so I add 1 H2O to this product side of the equation. Okay, I have 3 oxygens here and 4 oxygens here, so I need to add an H2O to this side of the equation, which I did. It's right here. The next thing I'm going to look at is hydrogen, and I'll do that with H+. So looking at this half reaction, I have 1 hydrogen here, and I have 3 on this side, so I added 2 H+ over here. Okay. That then takes me to my next half reaction. I have CrOH3 plus H2O, yada, yada, yada. It's all written the way it's supposed to be. I have 3 hydrogens plus 2 hydrogens is 5 hydrogens. And I have none over here, so I need to add 5 hydrogens to that next half reaction. Okay. And bear with me just a minute, I'll pause. Oops. I meant to pause the recording, but sorry about that. I really apologize about that. I had to check on my car, so that sucks. I'll try and cut that out. So that took us to adding 5 hydrogens right here. So I'm now in a space where I've done anything but oxygen and hydrogen. I did the oxygen and the hydrogen. So now I need to look at the overall charge. Overall charge on this half of the reaction is +1. Overall charge on this half of the reaction is -1. Okay. I have no charge over here. This is a 2 minus, 5 plus gives me a 3 plus total over here. So I need to make sure that I've added electrons for that. So the difference between the +1 and the -1 is 2 electrons. So I added 2 electrons here, and I need to add 3 electrons to this side of the equation to make them equal. So I put 3 electrons right there. Now I need to make sure I have the same number of electrons on both sides. So I have 2 that I added here and 3 that I added here. So I'll multiply this equation by 2, this equation by 3. Once I've done that, I have 3HO2 minus plus 6H plus 6E minus goes to 3OH minus plus 3H2O. Okay. I also have, when I multiply this one by 2, 2CrOH3 plus 2H2O goes to 2CrO42 minus plus 10H plus 6 electrons. Okay. Now that I've got my electrons the same, 6 on both of them, I can add and cancel. So when I cancel, I have 6 hydrogens over here. I have 10 on this side, so I cancel the 6 here and leaves me 4 on this side. When I look at my H2Os, I have 3 waters on this side, 2 waters here. So cross this out, those 1 water here. Okay, so that's what I'm looking at. And my electrons, of course, better cancel because that's what's supposed to happen. So now I can add those two together. I have 3HO2 minus that pulls down plus 2CrOH3, which pulls down. That gives me 3OH minus plus the H2O plus 2CR42 minus plus 4H plus, and that's all that's left. Now, this solution is basic. Okay, it said it was a basic solution. So now I have to do a correction for the fact that this is not an acidic solution. The problem with acidic solution is this H plus that I have. So I need to correct for that. And the way that I do that correction is to add the same number of OH minus as I have H plus to both sides of the equation. So if I slide this up, what you'll see is I added 4 OH minus right here, and I added 4 OH minus right here. Okay? These two come together to make 4 H2O, and then I'm left with the 4 OH minus over here. So looking at all of this, one other thing I can cancel. I have 4 OH minus on this side and 3 over here, so I only have 1 that's left over, and that's right there. So that brings me down to OH minus plus 3HO2 minus plus 2CrOH3 goes to 5H2O plus 2CrO42 minus plus 4H2O. And now I got to check that again. Oops. Hold on. This should, I don't know how I got it to work last time, but let's check where we are at this point. It's terrible. Okay, so when I look at the hydrogen, I have 1, I have 3, which gives me 4 plus 6, which is 10. I have 10 right there and 14. See, that doesn't make any sense. What the heck? Oh, that's right. We have 1 there. As a product. Oh, I need to add those together to give me 5, which I did, which is right there. Sorry, I already had them. I apologize. So I had the 4 here. I already had 1 here, so I added those together, and that gives me the 5 that's here. So the count that I had was correct. I apologize. Do this myself sometimes. So on this side, I have 10 H. On this side, I have the 1 oxygen. I have 6 there, so that's 7, and 6 here. 6 and 7 is 14, 15. My math is terrible. 5 there plus 8 is 13. And that's 13. I told you my adding is so terrible. So that's 13. I have 2 chromium, charge on this side. I have 2 minus, and this is 4 minus because there's 3 out in front, so that's a 4 minus. And this 2 times 2, 4 minus. So that is how we got the count that was there, and I apologize for that. It's terrible. Okay, so that was balancing. Now, it's a lot of steps. If you can get into the pattern of the steps, it will make it a lot easier to, 1, know what to do, and 2, be able to figure out where you went wrong. So one of the things you might have seen while I was doing this was, wait. I'm not sure where it canceled. This might have gone wrong over here. Because I've written all the steps out, I can see that. If I had just done it as one process, I wouldn't be able to see it. Okay, so this is why I do it the way I do it. Because if I make a mistake and I forget something somewhere, like I don't carry across the 3 when I do the multiplication, I do that sometimes. And I forget to multiply something by 3 and suddenly the count's off. I can go back and look at that step and go, oh, wait, you didn't do it for everything. So it makes it a lot easier to figure out where you messed up. So then you can fix everything after that. You don't have to start over. So what we're going to be talking about today, we'll talk about standard electrode potentials. We'll talk about the effective concentration on cell EMF. We'll talk about the thermodynamics of redox reactions. Then we're going to talk about voltaic cells themselves. Okay. So what I'm going to do first is go back to the redox lecture notes. Okay. I should have moved them, but I didn't. So I'm going to go back to the redox lecture notes at the very end. And we're going to talk about some of the things that are in these notes. So, starting our conversation with voltaic cells. Now, when we talk about voltaic cells, actually, just making sure there's not a slide before this one, sorry. Yeah, no. Okay, when we talk about voltaic cells, what we're looking at is any cell that is built as separation of an oxidation from a reduction. When we do that, we can measure how the energy that's generated from the movement of the electrons between one side and the other. It is traditional for us to put the reduction on the right. So Leo goes on the left. So the oxidation should be on the right side. That's tradition. If you get it wrong, it's not that big a deal, but other chemists won't know what they're looking at if you do it backwards. So your electron flow should always go from left to right. Okay. So we lose the electrons here, we gain them over here. So the reaction that I have in here, I have zinc sulfate, which is Zn2 plus, and I have zinc metal. Now on this side, I'm going from the zinc metal to the Zn2 plus. Now, there happens to be this solution in there already, so that's supported. Okay, so we just add more ions to this. Now, the reaction I have on this side is with copper, Cu2 plus, and the copper metal. On this side, we're going to go from Cu2 plus, gain those 2 electrons, and then come out to Cu. That's my reduction that's going to happen there. Now, what happens over time is as I do this reaction, and the electrons leave this side to come over here, this ends up being a positive, and this ends up being negative. Now, in nature, in reality, you have never seen this, and that's because it cannot happen. What we have to do when we build these cells is to include this thing called a salt bridge. So what you're looking at right here is a salt bridge. It contains K and Cl. So there's a cation and an anion. So when this starts to become positive, those Cl minus come out and come in here. When this starts to become negative, those K pluses come out and come in here to keep that charge neutrality. Okay, that is absolutely necessary. If you set up one of these cells and forget the salt bridge, nothing will happen. Absolutely nothing. It's one of the biggest indicators that you've forgotten your salt bridge. The other thing we have is that these two electrodes are connected by this wire that goes to this thing called the voltmeter. A voltmeter allows us to measure charge. And so what it's measuring is the energy that is generated from the movement of these electrons. And that is because of the differences in energy between the two states on either side. Okay. So we'll talk about what that means a little bit later, but this is what we're talking about. We have a voltaic cell, generally speaking, is any cell that separates oxidation from reduction. Okay, so anything that does that. Now, so this statement is not exactly correct. We'll get to that. All right, so this is a way that we typically see this. Now, they're not always separate beakers. I'll show you that in a little bit. We can do this slightly different ways, but we have to have two isolated solutions where these two reactions can happen separate from each other. Okay. So another way that we see this is in one container with a porous membrane between them. So this porous membrane will keep the separation between those things. It allows, the counterions to pass through it. So whatever other things were in here other than the ion in question. So if we're talking about the same system that we were talking about over here, where I have Zn going to Zn 2 plus 2 E minus, and on this side I have Cu 2 plus 2 E minus going to Cu. We have to have some counter ion that exists with the Zn2 plus. And what we saw over here on the other one was that this was SO4 2 minus that was present in both of these. Okay, so that was the counter ion. And what can happen for those two counter ions is that when we need to move the negative ion over to the cathode side, that can happen. All right, so we can move that SO4 across this membrane. We have to have some other kind of positive charge that we could move to this side. And so often we put something like sodium chloride in there or potassium chloride, something like that, so that there is some spectator ion that can move to balance charge, but is not involved in the chemistry. Okay, so that's what we see with this. So all this means is that you have this porous barrier salt bridge so that things can travel without needing the external salt bridge. Okay. Now that salt bridge is meant to keep things electrically neutral on both sides. Okay, so it maintains electric neutrality, because otherwise we would build up charge, negative on this side, positive on this side. Okay, we can't have it. So that's how that has to happen. Okay, so those are two ways we typically look at these kinds of cells. Now, we have another thing that we deal with, and it's called a cell notation. Okay, so it's a shorthand way for us to talk about what those cells that we drew on the last two slides will actually look like. So lazy chemists don't want to draw everything every single time. The cells that we've been looking at would be symbolized as Zn solid with a line here, Zn2 plus, and that's aqueous. Then comma, the concentration of that ion, which standard should be 1 molar. So 1.0 molar standard, 1 ATM is standard, and that's actually right here. But again, it's important that you know that. They can be other things, but standard conditions state that that's what it is. We should list it if we know it. Okay, so the expectation would be that there is a concentration here. All right. This line right here represents a phase boundary. And what I mean by that is this is a solid and this is aqueous. So they're not the same phase. So there's a boundary between them because of that. Now, that's one of the half cells that we looked at. Then we go to the other half cell. And so we have a double line that comes here because it means it's a different cell. So we're now describing what's on the other side. On the other side, we go from Cu2 plus, which is aqueous, at 1 molar, to Cu solid. Again, there's a phase boundary between them because they are not the same phase. So we know we have two sides. We know we have concentrations that need to go with anything that's aqueous or gaseous. We have this thing for two different cells. So all of that needs to be included. Typically what you're looking at is because we have a situation, we often go from a solid to an ion on the oxidation side and an ion to solid on the reduction side. We typically end up with a solid, ion, ion, solid. That's a fairly typical structure that we see, but it doesn't always happen. One of the things that we measure against is H2 being converted to H, okay? And so that's a gas that's converted to an aqueous component. But I can't use H2 or H plus as that electrode. And so there has to be something present to carry those electrons. And so we put in an inert electrode, such as platinum. And when we write that in that half cell, that goes on the outside. So we have our PT, which is our electrode, phase boundary to the H2 gas, phase boundary to the H plus aqueous. Okay, so your inert electrode will always have a phase boundary between it and the rest of this stuff. So it's always on the outside. Now, oxidation should be on the left, reduction should be on the right. Okay, so one other thing that we need to talk about is there are names for these two electrodes. Okay, so the two electrodes that I have over here, this one is called an anode. This one is called a cathode, right? Now, how do I know that? Well, let's think about this. If we write it the way we're supposed to write it, the oxidation occurs on the left, right? So oxidation, and it goes with the anode. Now, let me write the other one. The reduction occurs on the right, and it occurs at the cathode. And the way that I always remember this is that it's a red cat. So reduction occurs at the cathode. And then if I need something to think about, these are both vowels, so they go together. Okay, so that's the way that my brain works with that. It's this basic red cat. Okay, reduction occurs at the cathode. That means that the oxidation has to occur at the anode, and that makes sense because they go together because they're both vowels. Okay, so that's how you do that. So we have this species, which is being oxidized. It is therefore a reducing agent. It is also the anode. Over here, we have a species that is reduced, and that's a Cu2 plus. It is the oxidizing agent, and that occurs at the cathode. Okay, remember that we always talk about the oxidation and the reducing agent with whatever was the starting material. Okay, so whatever's on our reactant side. So here it's the metal, here is the ion that's done with. Okay, so remember to keep those straight. Okay, in my head, this is a very big circle of things. So if I can keep track of where the electrons are lost, lose electrons oxidize, oxidation occurs at the anode, and that is the reducing agent. The reduction occurs at the cathode. That cathode is where that reduction occurs, so the electrons come in there, so gain electrons reduce. It is seriously this big cycle that I go through all the time. Hopefully you won't need to do that, but for me, that's the only way it works. Okay? So that's another thing we had to talk about. So this happens at the cathode. This happens at the anode. we get electrons going from the plus charge since the current is defined as flowing in the opposite direction from the electrons. It's just physics and chemistry couldn't agree on that. So if we want to talk about the balanced chemical equation for this process, we have to think about the fact that we start with Zn solid, and that goes to Zn 2 plus. Okay, that's one of my half reactions. The other half reaction, or reactant, is Cu 2 plus, and that goes to Cu solid. Now, how do I know that? Because this is written before this, and this is written before that. So reactants, products, reactants, products. So that's how I know what goes down here. I know that both of these have 2 electrons in those processes, so this as written is balanced. Okay. So that's my balanced chemical reaction for this process. And that talks about my cell notation. Okay. Technically speaking, this right here should also say 1.018. I forget. So that should also be there. All right. So some examples. Copper solid going to copper and silver going to silver solid. Okay, so those are the 2 reactions that I have listed there. Copper solid going to copper. It's a 2 electron process. And that's silver solid, which is an ion going to silver. So that's what this says. Now it's a 1 electron process for this. So that's the half reaction for that. So remember, the half reactions, we don't necessarily think about them in terms of how many electrons do I need in the total. Okay. So that's the 2 half reactions. So I have my Cu solid going to Cu2 plus 2 electrons, lose electrons oxidized. At the cathode, I have Ag plus an electron going to Ag solid. Okay. And I multiply this by 2 to get 2 electrons so that they're both the same. If I do that, now I have both the number of electrons being 2, then I can add them directly together to get 2Ag plus Cu going to 2Ag plus Cu2 plus. And so my cell notation would be Cu solid in contact with Cu2 plus. And again, I just put concentration because I didn't know what it was. It's different cell, Ag plus, aqueous, in contact, physical boundary with Ag solid. Okay, so that's what we're talking about there. All right. Now, when we talk about this next one, I have magnesium solid going to magnesium, which is MgS going to Mg2 plus. Okay. I haven't included the electrons here. It's a problem, but okay, we'll deal with that. And then iron 3 going to iron 2. So we go to Fe3 plus going to Fe2 plus. Now I know that this particular process right here, so this first one, I get 2E minus out of that. In order to make this go from Fe3 plus to Fe2 plus, I have to add 1 electron on this side. So that's why I multiplied this by 2 to get 2 electrons in both halves, and therefore I'm going to add them together. Okay, that would give me Mg solid plus 2 Fe3 plus Mg2 plus 2 Fe2 plus. Okay, and the cell notation for that would be Mg solid phase boundary, Mg2 plus aqueous, different cell, Fe3 plus, which is aqueous, comma, Fe2 plus, which is aqueous, because we put a comma if they're both in the same phase. Then I need a boundary and platinum, because I don't have a solid. So I need that platinum that can carry the electrodes, or the electrons. Okay, so again, that's my inert electrode. Inert electrode is there. Now, I know a lot of people get overwhelmed at this point. How do I know how many electrons it is? How do I know what's this? How do I know what's that? you have this. So this table that you guys have got should help you with that. Okay. So I can look and I can see now this one told me iron 3 to iron 2, right? So iron 3 to iron 2, there's an electron right there. So that tells me where the electron goes, okay? In this reduction, right? Remember, these are all written as reductions. When we talk about the Mg, all I have to do is find Mg in the table. And he's down here, Mg2 plus 2 electrons goes to Mg solid. Now I know that Mg, because he's in the second column, should be a 2 plus ion. I got it. But if I don't remember that, or I'm overwhelmed with all this stuff, I can use these half reactions to help me, okay? So use what you have available to help you. It is never wrong to work with the half reactions that exist there because they're already balanced, they are correct, so you can always use them. Sorry, getting my screen share back. Okay. Hopefully that will work. Gonna work? Maybe not. I hate it when that happens. There we go. So again, learning to use the information that's available to me to assist me with this process. Okay. And that's all I'm trying to do, is to assist in that process. Now, I have some practice that is here, and I have already posted this. So I'm not going to walk through this. This is the exact kind of thing that we were doing on the last slide for the two things there. Okay. I actually talked about how you tell which one is the anode, which is the cathode. So there are two slides in here that are about the experiments you would do in person. So you don't have to worry about those. And we actually changed one of the experiments anyway. So you don't need to worry about the rest of what was in the redox lecture. So now we can go back to what was in the Voltaic Cells lecture. And we left off here. That's it. That's so weird. Okay, never mind. Not important. So when we talk about cell potential standards, now electrons flow spontaneously one way in a redox reaction. So it will happen from high potential energy to low potential. That's what occurs. The potential difference between the anode and the cathode in a cell is called the electromotive force. So it's how much energy those electrons are creating when they move. It's also called the cell potential, and it's designated as E cell. Okay, so that's a symbol for it. The standard cell potentials are always listed as reductions. That's what you see in this table. Every single thing that's in here is a standard reduction potential. Okay, that's how it's listed. So these are always reduction half reactions. Those values are independent of the stoichiometry of the reaction. Okay. What that means is that if I multiply one of these things by 2 to get the same number of electrons, to add them together, I do not change the value that is listed here. So I don't multiply that. I never do. With these, you never change them. Okay. There is one exception, and I'll talk about that in a few minutes. Now that's measured in volts. 1 volt is 1 joule per coulomb for people who want to know. That's how that works. The reduction potentials for many electrodes have been measured and tabulated. This is the table that I'm talking about. The values are compared to reduction of hydrogen as a standard. So if I take a 2H plus aqueous plus 1 molar plus 2 electrons to give me H2 gas at 1 atmosphere, this is what I measure everything against. So I can only tell the relative differences between things. I don't have like an absolute value for them. That's not how this works. So we don't start at 0 and go up all the time. That's not how this works. It's either positive comparative to hydrogen or negative comparative to hydrogen. So that is information you need to understand. Everything is measured against this. And so it's always a relative difference from there. That reference is called the standard hydrogen electrode, and it's referred to as SHE. By definition, as the standard, the reduction potential for hydrogen is 0 volts. You will see that in this table if you come to where we talk about hydrogen. Hydrogen is right here, and that is 0. Okay? So anything that's above this is a better reducing agent than hydrogen. Anything that's below it is not as good. Okay, so the same kind of thing that we saw with the activity series, but now we have values that go with that. Okay, so that in my head made things a lot better. I like numbers. So that's what we're talking about in terms of those cell potentials. That's what they are. That's how they're defined. That's how we get these numbers that are in this table. Okay. It doesn't tell me what I do with it, but it tells me what they are. So again, we have tables of these things. These guys are stronger oxidizing agents. They're better at causing oxidation because they are very easy to reduce because they're up here in the table. Okay. These are weaker reducing agents, stronger reducing agents at the bottom. Okay, so that's what we're talking about. There are lots of different charts that you can look at. Okay, so lots of different ways that this is done. It depends on what you're looking at, what you're going to get. The table that you've been presented is what we thought were the most important reactions for you to work with. And that actually comes from this book called the CRC. And I'm actually going to show you a CRC just because I feel like doing it. And I'm in my office, so I can't. So this lovely book right here is called the Chemical Reference Company's Book of Standard References. And I mean, it's been around forever. This is 74th edition. And I know they have more ones, but it's got like all of the chemistry and physics stuff. So the values that we've measured for all of these things are in this book. These books are great and they exist for a lot of stuff. I'm actually working on a version for plastics testing at the moment. But it's where you can pull a lot of information together. And then if you need to find something like a value for something, you can always go to your CRC. Okay. If you need to know which standard is used for what kind of testing, there's a book for that too. So there was a lot of information in those books and they're incredibly, incredibly important. So they are ridiculously expensive, but they are always available at the library. And it doesn't matter which library you go to. I've never been to a library that didn't have one. So, and unfortunately, they do not put them online unless you want to pay an arm and a leg for them. So it's not easy to search through them. You have to actually open the book and find this stuff. So when I was a student, I actually carried my CRC with me just because I needed values often enough and I thought it was worth it. So, but that's where your values come from. Now, those standard cell potentials for standard conditions, we can use the following equation to calculate the E for the cell. And that E naught for the cells, so this naught means standard conditions, that's the energy of the cell is equal to the standard energy for reduction at the cathode minus the standard energy for reduction at the anode. Okay. This assumes that you're using the values exactly as they appear in the table. Okay. So if I were to look at this thing that we've been talking about, the reaction that we have for our anode, the value for the anode is negative 0.76 volts. So I look this up and that zinc thing. Where's my zinc half reaction? I hope it's over here. Yeah, Zn2 plus 2 electrons goes to zinc and it's negative 0.6762. I didn't include the third digit. So for the cathode, we were looking at the copper half reaction. And so if I come down here, oh, that's, yeah, no, it's not the right one. So it's up here, Cu2 plus 2 electrons goes to Cu solid, and that's 0.34. So those are two values exactly as I read them out of the table. So if I'm doing this math, I take the 0.34 minus the negative 0.76, because I always do the cathode value minus the anode value. And that means that I end up with 1.1 volts. Okay. Now, I mentioned to you that we don't ever change these things. If you're on the interwebs, you may see somebody who says, well, that's the anode, so we flip the value. What they mean is that instead of doing the calculation like this, what they're doing is that they calculate E naught cell as the E naught reduction for the cathode plus the E naught oxidation for the anode. So they find the oxidation value. Now, what is the oxidation value? It's the exact same thing. We just changed the sign. So instead of having this like this, we'd have this as 0.76 volts when we talk about the oxidation value. For some people, that math is easier. For me, as a student, it was much easier to remember. If I flip it, I change the sign, and then I just add the two values together. So I'm totally okay with that. But if it's easier for you to just use this equation as written, that's perfectly fine. This is the one that you will find in the useful equations on the test. This is the version. But if you want to use the other one, if you want to flip the sign and then add them together, that's totally fine. I just need to see your work to know that's what you did. Okay. And this is that alternative that I was talking about right here. All right. So if you flip the sign, you can then add them together. And for me, again, as a student, that was easier. So either way works. You should end up with the exact same number. Okay. Now you got to be careful, because you can't just say, well, I need to subtract the negative number, because it doesn't always work that way. We don't always set these things up so that one's a positive value and one's a negative value. So you've got to be careful how you think about it in your own head. All right. So again, the more positive the value of E naught reduction, the greater the tendency for reduction under standard conditions. So the strongest oxidizers have the most positive reduction potentials. If they want to be reduced, they cause oxidation in other things more. The strongest reducers have the most negative reduction potential. So they're down here. Okay. A reducing agent causes reduction in something else. Oxidation agent causes oxidation in something else. A material on the left of a half reaction will react with any material below it and on the right. So what does that mean? Well, if I'm looking at these things that are here, I can see that Cl2 plus 2 electrons goes to 2 Cl minus, right? And it says that anything that's on the left above something can react with the thing that's on the right below. So I know that Cl2 can react with H2 to give me 2 Cl minus plus 2H plus. That absolutely will happen. And that's based on those energies. Okay. Absolutely will happen. Now, can aluminum ion reduce lithium solid? Well, aluminum is right here. Lithium solid is here. So yes, that is absolutely true. What about the lithium ion? Can it reduce the aluminum solid? Or could this Al3 plus do that to the lithium ion? No, absolutely not. That is not something you can do. It's on the wrong side. Now, what can that lithium ion reduce? Absolutely nothing, because there's nothing below it, not in this table anyway. So based on the information that you have available on this slide, there's nothing that it can reduce. And you're limited by the information that you're given. So if I give you something that looks just like this and it doesn't have a value in it, there's nothing you can do with that. Okay? Okay, so you tell me, I don't know, it's not here. Because that happens. Now, hopefully it doesn't happen to you on the test, but that's the thing. Okay. You may run into that if you're out in the world and somebody asks you, can this happen? If you don't have a value, you won't know. So all you can say is, I don't know, but I could find out, because you could run the reaction and see if it works. Okay. So that's something that to be aware of. So people will ask you about things and then may not be tabulated, so you may not know. All right. So questions. Okay. Now, how do we use these standard reduction potentials? Okay, so what we want to do is we want to look at the things that I've asked you about down here. So fluorine gas and lithium, lead, manganese, oxygen and acid, mercury, silver, and nitrogen. And I want you to find those things in the table and then talk to me about that. So we're going to calculate the overall reaction. You're going to decide which one is the anode, which one is the cathode, what the overall cell notation is, and what the E naught for the cell is. Okay. So I want the overall reaction, the anode half reaction, the cathode half reaction, the cell notation, and the E naught cell. So the first one that it talks about is fluorine gas and lithium. So I have to find in my table fluorine gas. Fluorine gas is all the way up here at the top. It's F2 plus 2E minus going to 2F minus. The value for that is 2.866 volts. So that's one of the half reactions that I'm dealing with, and that's the fluorine gas. Now I need to find lithium. And you may remember that lithium is down here at the bottom. Lithium is a solid, so that means that I'm going to be going from lithium solid to lithium ion. So I'm going to write this in that direction. So that's the half reaction for the process I need. All right. The energy that's associated with that is negative 3.040. And notice I haven't changed it. I've written it as the value for the reduction. Okay. And that's the lithium. Now it asks me, because I'm reacting this with this, what's the overall reaction? Now, in order for me to do that, I need to have 2 electrons. So I need to multiply this by 2, I need to multiply that by 2, I need to multiply that by 2, and then I can add these together. And so the overall reaction for this would be F2 plus 2Li going to 2F minus plus 2Li plus. Okay, so that's the overall reaction for this process. If I want to look at what is the anode, well, the anode is where the oxidation occurs. Lose electrons, oxidize. This is my anode. If my cathode is where the reduction occurs, gain electrons, reduce, this is my cathode. Okay, so overall reaction, anode and cathode. What would be my cell notation for this? I would have platinum in contact with F2 gas in contact with F minus. That is then in contact with the Li ion and the Li cell. Okay. Now, did I need that platinum electrode? Absolutely. It's because I have a gas. So I have no solid that I can connect to, so I need that platinum electrode somewhere. All right. Is that exactly balanced? But no. And that's something that we often see. Okay. There may not be the same number between here and here. Now, can you write that? Absolutely. If it makes you feel squirrely to not do this, fine, deal with it. But you have to understand that the concentration that should be here is the concentration of the F minus ion and not the 2F minus. Okay, so that's one of the reasons that we don't do it that way, because we need to know what the concentration of the F minus is, and that's why we list it that way. Okay. Now, if I want the E naught for the cell, all I would do is take these two values and add them together. That's what I do. Do I actually add them? No, I don't. So that, oh, sorry, the E naught cell is equal to the E naught production for the cathode minus the E naught production for the anode, which then means we would have our reduction for the cathode 2.866 volts minus the negative 3.040 volts. Okay, and that would give me a huge value. It actually does. What is that value? (2.866 minus negative 3.040, and that gives me 5.906. Okay, so that's the voltage for that particular cell. Now, could I have added them? If I'd done the math right and I put this down as a positive value because I flipped this, then I could have added them, yes. Okay, so either way, again, that's entirely up to you. And I said add because that's almost always how I do it. So I apologize for that. But that's how we calculate that value. All right. Now, I have put the rest of these online already. I have posted this already. So I will let you look at that and take a look. If you have any questions about what I did or why I did it, please talk to me about it. Okay. So that's one way we could use our standard reduction potentials. We can also look at this and say, okay, calculate the standard reduction potential for the following combinations. So I have 2Ag plus Cu going to 2Ag plus Cu2 plus. So if I look over here in this table, or I flip to the one that I actually have because it's a little easier for me to see, Ag plus going to Ag solid right here, and that's 0.80. Okay. If I then have to find that copper one, where is that copper? So I have Cu2 plus long. Oh, that's going to Cu1. I don't want to do that. So notice there are two things that I could do here. I could go from copper 2 to copper 1, or I can go from copper 2 to copper solid. Because this reaction is from copper solid to copper 2, I actually need this value right here. So the Cu2 plus 2E minus going to Cu solid. And the value that I see for that is plus 0.34. So I've looked up those two values. I know that I'm going to take the E naught for the reduction, which is this one. So I will have my E naught cell is equal to the E naught reduction for the cathode minus the E naught reduction for the anode. And in this case, that would be the 0.80 volts for the reduction. That's one right here, minus the one for the anode, which is this value right here, the 0.34 volts. And notice I said we have to be careful because it's not always negative. This is one of those cases. So if we're looking at that number, 0.84 minus 0.3, oh, sorry. Zero minus 0.34. And that gives me 0.46. Okay. So that's what we're looking at for that. So you've got to be cautious with your values. And all we had to do was look up those two half reactions. Because I don't have to worry about the stoichiometry, it doesn't matter that this is only one electron and this is 2 electrons. I don't change this value when I use it. So I actually ignored that. I just make sure that I have them in the right direction. So I know that which one is the reduction for the cathode and which one is the reduction for the anode. That's all that matters. Okay. And I've put the other ones up. The one that I'm going to talk about, though, is this one. What you'll see in this table and what you'll see in the one that's on. Yep. Oh, so both this table and this table have no value for platinum. Is there a value for platinum that you can look up? Yes. But we don't have one. And we have stated that platinum is an inert electrode. So if this is something that you run into, you can do one of two things. One, I have no value. Or PT. So I can't calculate. And actually, I have no idea which is the reduction, which is the oxidation, blah, blah, blah. So I can't calculate that. The other thing I could say is that PT inert electrode, no reaction. Because given the information that we've been talking about, I wouldn't think that there would be a reaction. Now, I can force one. I can absolutely force it, but that's not something we should be talking about here. So this is something that you can answer in that way, and that's why that answer is okay. So questions about what we've done so far. Now we need to talk about what are the implications of the E naught for the cell. So I calculated this value, right? And I said that electrons flow spontaneously in one way in a redox reaction from high to low potential. Well, per chapter 17.2, which we'll be talking about in the next few lectures, a spontaneous reaction is a reaction that does occur under a given set of conditions if we leave it alone. If it does not, it is non-spontaneous. So all I have to do is put it together and it will go. If it won't go under those circumstances, then it's non-spontaneous. Okay. So if I'm talking about spontaneity, when we talk about this, we're talking about, does it have the energy available to make this happen? And the E cell can tell us if it's a spontaneous reaction. So the E for the cell is not exactly the same as the E naught for the cell. Okay, it's close. When this thing is missing the little zero right there, that means it's a non-standard condition. Okay, so it may not be 1 atmosphere, one molar for everything in the universe. That may not be the case that we're looking at. Right? So we need to look at what the E cell is, not just the E naught cell. Right? So we can calculate that cell. We'll talk about how we do that in just a few minutes. But if that E cell is greater than 0, then it's a spontaneous reaction. And that's termed a galvanic cell. Okay? It's just the name that was given to it. Ancient. It's not important how it was derived, at least unless you want to go figure it out. But that's what we call the spontaneous cells. If E naught cell is less than or equal to 0, then it's a non-spontaneous reaction. Now, if it's less than 0, we can do it in the reverse direction, and that's called an electrolytic cell. Okay? Meaning I need to apply energy to make this happen. So Voltaic refers to any cell regardless of spontaneity. Galvanic cells are the spontaneous ones, electrolytic cells are the non-spontaneous ones. Now, if a reaction is non-spontaneous, it can't occur on its own. We can make it happen. We have to supply energy to make that happen, such as recharging a battery. So we apply energy to that to make that go backwards. Okay. So if it's non-spontaneous, it can be driven in the way that it's written. But if we flip that reaction, turn it around, the one in the reverse direction is spontaneous. Okay. So The one in the reverse one, so one direction is spontaneous, the other one is not. Okay, and that's based on the energies that we have. And we'll talk about that in more detail in the next couple of lectures. So cool with that. So if E is greater than 0, it's spontaneous. If E is less than 0, it is non-spontaneous. And we've talked about standard conditions, 1 molar, 1 ATM. But if it's not, then we can calculate it a little bit different. Okay. There's a correction that we can do to the value that we calculated under standard conditions. Now, and the other thing, standard conditions also for these applies to 25 degrees C, 1 ATM for gases, and 1.0 molar for aqueous solutions. It has to be at room temperature, 25 degrees C. Notice that is different than the way we defined STP for gases. They're different standards, so it's different temperatures. Okay, be aware of that. So we can calculate that standard cell potential, the E naught cell, using the values in the table. We absolutely can. And then we can do a correction for that based on a couple of things. One, concentrations are not the same, which is how we would do this. So different concentrations. Or we can set up for different concentrations and different temperature. I'll show you that equation on the next slide. All right. So it could be that one thing was messing, I took away product, and so I don't have enough product. And of course, if I don't have enough product, then I'm going to want to go forward. And so that changes the drive for that reaction. So we have to calculate Q. Q was related to K. So Q is equal to the concentration of my products over the concentration of my reactants raised to their stoichiometric coefficients. And this is at any time except equilibrium. Q applies to any other time. If we're at equilibrium, then they're the standard values. Okay, so that's that's the kind of thing that we're talking about. Right? So I can calculate a cell voltage for non-standard conditions to see if a non-standard cell is spontaneous or not. We can do that. Okay, so we have to be able to calculate that Q. So let's see what that can look like. Now, there is another form of this equation, and I'll show it to you right here. E is also equal to E naught minus RT over NF. So if I'm at a different temperature, I can correct for that using the temperature, the number of electrons, the R value, which is a different R value, it's that 8.134, and the Faraday constant. Okay. If I'm at the right temperature, this reduces to this. So it would just be 0.0592 over N times the log of Q. Okay. So if we're at standard temperature, which is always the way I'm going to ask you. So never non-standard temperature. So always this version. Both of these are on the test. This is the one you primarily work with. Okay. So let's consider the following cell diagram. I have magnesium solid going to magnesium sulfate, which is 0.4 molar, and nickel sulfate, which is 0.6 molar, going to nickel sulfate. I want to calculate the cell voltage at 25 degrees C. So I know that E cell equals E naught cell minus 0.0592 over N log Q is the equation that I need. N is the number of electrons that are transferred in this process. I know that to go from Mg solid to Mg2 plus, that is a 2 electron transfer. Going from Ni2 plus to Ni is also a 2 electron transfer. So N is equal to 2. Now my Q is equal to my products over my reactants. So this might take a minute, but if we take this cell, the cell notation, I know I'm going from Mg solid to Mg2 plus. And I'm also going from Ni2 plus to Ni solid. Remember, reactant, product, reactant, product. So that's how I got this statement right here. And that means that my product concentration is the Mg2 plus. So Q is equal to the concentration of the Mg2 plus times the concentration of the Ni2 plus. Because this is a solid, neither one of those will appear in that, and so it would just reduce to this. And that's where I put in this value down here. So Q is equal to 0.4 over 0.6 because the Mg is 0.4 and the Ni is 0.6. So that's where we get that. Now the standard E naught for this cell is 2.12 volts. And I didn't walk through that because I assume at this point that you're familiar with pulling those values from the table and calculating a standard cell. And if I plug all of that stuff into my calculator, so I take, the E naught, which is 2.120, minus the 0.0592 divided by 2 times the log of 0.4 over 0.6, I get 2.125. Okay, so that's how that works. Now if I change, how does the voltage change if I change Mg2 plus to decrease it by a factor of 4? So I take this from 0.4 to 0.10, that's this. So now I would replace in the Q 0.10 over 0.60, then that voltage changes to 2.143. And let's think about that for a second. If I have made the Mg2 plus smaller, this is smaller, the reaction should go forward, which means that the energy force to do that should be higher, and it's more spontaneous. That makes sense to me. If I take and I change the Ni2 plus and I reduce that concentration, so I take the 0.60, decrease it by a factor of 3 to give me 0.20. So initial condition 0.40 over 0.20. I now have less of this. I have the same amount that I started with. And so this reaction should shift this way and be less spontaneous, which is why I have a smaller E. Because it doesn't want to go as far forward. I just don't have as much drive to. Now, if I do both of those changes, if I change the Mg2 plus and the Ni2 plus, so I've changed both of these things, then the question becomes, well, which direction is it going to go? Because I've changed them both. So I do the calculation and I end up with the cell being 2.129. So if it was 2.125 before and 2.129 now, it's going to go forward. And that actually makes sense to me because I've changed the Mg2 plus more than I changed the Ni2 plus. So it should go forward. Okay, so mathematically that makes sense to me. Okay, decreasing the product makes the reaction more favorable. So you have a higher E cell. Decreasing the reactant makes the reaction less favorable, lower E cell. Okay. We can do this again when we talk about an Ag electrode in a 0.15 molar AgNO3 and an Ag electrode in a 1.0 molar AgNO3. Oh, wait, that's weird, isn't it? So let's talk about what that actually looks like. Actually, I didn't want to do this. So if I have Ag as a salt plus an electron going to Ag plus, and that's happening on both sides. So this is my half reaction on both sides of this half cell, and they're connected. One of them has 0.15 molar, and the other one is a 1.0. We call this a concentration cell. So if I were to draw it, salt bridge, this electrode right here is Ag, so it's this one, G, this is Ag plus, this is Ag plus. And the way I've drawn it, I'm just going to put 1.5 here and the 1.0 here. Okay, so I want to measure what is the force between those two cells. Okay, interesting, right? So what would the E naught cell for this be? Well, one of these has to be the reduction, one has to be the oxidation, right? So if I have Ag solid plus an electron going to Ag plus, and Ag plus plus an or Ag plus, and that's Ag plus plus an electron, and then Ag plus plus an electron going to Ag solid. If I add those two together, they cancel. They do. And if I were to use the value for the E, I would have 0.22 volts minus 0.22 volts, which is 0. So if there wasn't a difference in concentration, this would have no drive at all. There's no, it wouldn't move. But because my concentrations are different, then I have an ability to move. Now I have to look at what I'm looking at here, okay? So here, this side, as I've drawn it, is the Ag solid going to Ag plus an electron. Lose electrons oxidize, that has to appear on this side. So the concentration of the Ag plus here is this. If we look at our reaction over here, we're talking about the Ag plus the electron going to the Ag. This concentration is 1.0 mole. So my product is the 1.0 molar and my reactant is the 0.15 molar, right? So if I take my E naught cell, or my E cell, that's equal to the E naught cell minus 0.0592 over N. This is a 1 electron process, so over 1 times the log of the product, which is 1.0 over 0.15. Now I know that this E naught cell is 0, so what I'm actually calculating is I would take negative 0.0592 divided by 1 times the log of 0. Sorry, wrong one, kind of backwards. 1.0, my product, divided by 0.15. And that ends up with this correction factor here. So this is the driving force that I have for this. So as it's written, it doesn't want to go that way. This is negative. So it doesn't want to go the way that it's written. What it wants to do is go the other direction. And if we think about this for a second, that should make sense to us. The tendency with a difference in concentration is to want those concentrations to be equal. So if my higher concentration is here and my lower concentration is here, I should want for the concentration of the ion here to go down. So I want that concentration to go down, and I want this concentration to go up. Okay? So that's why I would have the driving force in that direction. Okay, because I want to even out those concentrations. All right. So that's how concentration cell works, is to have different concentrations of the same thing on both sides. And in a pinch, I can use that to generate energy. Not a lot of it, but I can do it. Okay. Now, another practice when we talk about concentration. So the value for E naught cell for the following reaction is 1.1 volts. We calculated that. What is the value of the E cell when the concentration of Cu2 plus is 1 and the concentration of Zn2 plus is 0.025 molar? We're talking about Zn solid plus Cu2 plus going to Cu solid plus Cn2 plus. So again, my product Zn2 plus, or my reactant, which is a Cu2 plus, this one being 1.0 molar, this one being 0.025 molar. Okay, so if I put in my E0 cell, which is 1.10 volts, minus the 0.0592 over 2, because it's a 2-electron process, times the log of the 0.025 divided by 1, that's equal to this mathematics right here, which gives me 1.14 volts. So very slight increase as we do that, because I want to make more product. So very slight increase for driving that reaction in the forward direction. Okay. This is another version of that, and I want to show you this one because it's a little bit different. Now, I've calculated the cell potential for this as 0.189 volts. And what's the value of the E cell given the concentrations as shown? So I have 4H plus 0.10 molar, Fe solid 0.60 molar, NO3 minus goes to Fe3 plus 1.0 molar, and NO at 0.05 or 0.50 molar, and of course the H2O liquid, so I'm not concerned about that. So I plug in my E0 cell. I know this is a 3-electron process because I'm going from Fe to Fe3 plus. I put in a log of the products, so Fe3 plus 1.0 times the NO, which is 0.50, over the reactants, 0.10 to the 4th, because it is 4 of them, and 0.60 to the 3rd, because there are 3 of those. So you've got to remember the stoichiometry when you do these things. So your Q has to take that into account. And so that gives you this expression right here, which then gives you this value for the overall cell reaction. Okay. Things like this can be very complicated because it depends on how much of what you've got, those kinds of things. Obviously, there's a pH dependence for this. So we have to be concerned about some of these things when we do this. So remember to take into account your stoichiometry. It applies here too. I have posted this one. Any questions about any of that? Now, I want to talk about thermodynamics. The thermodynamics is the movement of things due to their thermal properties. That's what that thermo and dynamics breaks down to. We're going to talk about that a lot in the next couple of lectures. That's the entire content of what we talk about for test 3. It's related to the spontaneity of a reaction based on the energy and the disorder in it. So I always forget how to put it until I'm talking about it. So if a reaction is spontaneous, it occurs without any action being required. If that's true, the value of delta G, the free energy of the reaction, is negative. That is a definition. We'll come back to that. For now, understand that E cell can tell us if the reaction is spontaneous as written. If a reaction is non-spontaneous, it requires an input of energy to proceed. If that is true, the value of delta G is positive. In the case of Voltaic cells, we can tell if a reaction is spontaneous by looking at the value of the E cell. We told you this. So if E cell is less than 0, it's non-spontaneous. If E cell is greater than 0, it is spontaneous. And so I know that if E cell is less than 0, delta G is greater than 0, and it's non-spontaneous. If E cell is greater than 0, then that delta G would be less than 0, and that would be spontaneous. Okay. Now, delta G is related to E through this equation. So the standard and the non-standard, both of them are, I can get delta G by taking the number of electrons times the Faraday constant times that E naught cell. Okay, so I can calculate delta G from E, I can calculate E from delta G, both of those can be done. Right? So that is something that we need to keep in mind as we move forward. These E cells do matter, and we can use them for other things. We also know that that E naught cell is related to K. Okay. So if my E naught cell is positive, then it favors the formation of the products. I want to go forward. And that means that my K is greater than 1. Remember, K had to be greater than 1 if we had more product than reactant. And my delta G is negative, because we just talked about that. If my delta G is 0, K is equal to 1, and that means that I have no E naught cell. They're equally favored. And again, if my delta G is positive, my K is not greater than 1, then this E naught cell is negative. So it's not spontaneous in the forward direction. Then that means that K is very tiny. I have more reactant than I do product. Okay, so that favors the formation of the reactants. So all of these things are connected. All of the things that we've talked about. All right. This doesn't really include the rate portion of it. That doesn't connect as direct away as everything else. But all of the other things that we've talked about this term, K that we did for the first test, the E that we're doing for the second test, and the delta G for the third test are connected. Right? Now, this diagram is not on your exam handout. So the two equations are, but the diagram is not. Okay. And I don't, we can, and I don't use this one really. So we do this one and we do this one. But this shows the relationship. If I have E naught cell, I can get to K or I can get to delta G. If I have delta G, I can get to E, I can get to K. If I have K, I can get to delta G or E. All right. All of those things are connected through these relationships. Okay. So as we move forward and we start talking about all the things that go into delta G, we'll be looking at how these things are related. All right. So questions about that? Yes, that is a preview of coming attractions. These are some sample questions that I gave. I have posted all of this, so I'm not going to go through this right now. Here's some more practice. I also posted this. This is a little more complicated, so this takes a little bit more, but the explanations are there for what I did and why I did it. Okay. So any questions? By the way, this will not be a test question. This is meant to push your understanding so that you can see those connections in clear way. So that's the idea. So any questions, comments, problems? I will get this recording posted as soon as I can, and then you should have everything you need for the second test. Let me know if you have questions. Thanks, guys. I appreciate it.